Should I start with the good news or the bad? What do you like?
Both.
All right, the good news is no homework this week. Bad news, we're going to start doing some introduction to some hypothesis tests today, but you're going to hear it like 3 or 4 or 5 times over the next couple of weeks. So it's going to click. Sometimes maybe it'll click today, or if not today, next week, but definitely by the week after for sure. That's the only bad news I have. So I'm going to kill my face. There we go. And share. Let's start with math practice. Um, Nice job, everybody. Let me start with actually status, which might be the a record, in terms of um, yeah, I think just this is the most green I've seen going through descriptive statistics too, in probably 10 or 12 classes, I bet. So really nice job, guys. I'm gonna help out the people that are red. Need help? Just let me know. I'm in anytime, any place. Today, first week we did descriptive statistics. 199, 172 with a range of 27. So, the whole idea of Six Sigma is just decreasing the amount of variation in a process. So this process is my health. And it's one of the ways we measure it is my weight. We're going to throw in blood pressure and since 2006, we're going to throw in heart rate, I think 2006. I take it every Friday, first thing when I get up. These are the instruments that I use right there. And then you look at this time around, we went from a range, actually 06, 25, these are incorrect. Um, so we went from a range of 27 to a range of 12. It's kind of nice. The mean went from 184 down to 177. So, the bell is getting thinner, smaller and smaller, as you can see, because the max was at 199, the min was 174. Now we're like 172 and 184, so it's kind of going in the right direction. Um, and then the data pack, again, if anybody has any trouble, sounds like Bev's all set. And I'll see you tomorrow. I think it'll be helpful because there's a bunch of things on that data analysis pack. You pop it open that we're going to be using. Even there's some hypothesis test stuff when we do some regression. How many samples do I need? All the formulas are right here. So it's going to be very useful, I think. It'll be fun to use. And it's just a couple of clicks away, getting the same information. Again, no homework this week, but that's what it looks like. And so let me jump right into this fun, fun stuff. And it's basically an introduction, this like the 6 steps. I think I have 7 here, but on how to do a hypothesis test. So again, the thinking here is that we're always going to be trying to make our data talk and tell us something instead of just sitting on the page doing nothing, right? Staying silent. And one way to do that is once I have data that is normal, in other words, I can predict it's a bell-shaped curve. It's not all over the place. It's kind of predictable, as you can see with the weight data. Then I can start making asking the data some questions. And that's what hypothesis testing is. So I'm going to give you a little break from the weight right now, and we're going to talk about the average temperature since 1950 in July in the state of Connecticut is 87.5 degrees with a standard deviation of 3.5 degrees. So that means, the average is 87.5. And if it's not 87.5, then the average away from it is about 3.5 degrees since 1950. So that's, quite a bit of data. It's 75 years times 31 days. It's a pretty good set of data. And let's pretend that the temperature last July 7th was 94 degrees, which seems a bit warmer than 87.5. So the question we want to ask the data is, was that day's temperature statistically significantly different than the average for the month of July. And I want to know with 95% confidence. So I'm going to explain all these different pieces of this statement. So when we talk about statistically significantly different, that means, if we do some math, do a little bit of math, as you can see on the page here, it's going to tell me if it's statistically different. It may not be practically different, which means does it feel warmer or feel colder? It might not be practically, it may be practically different, but may not be statistically significantly different. Okay. So that's the key is we're going to kind of apply in a 95% confidence level. We could pick pretty much any confidence level we want. You can go, most commonly used is 90, 95, or 99%. So we want to know with 95% confidence was 94 degrees statistically significantly different for the month of July in Connecticut since 1950. So the steps are pretty much going to be all the same for every hypothesis test we use. And here's a list down here. You'll see them in the PowerPoint too, of all the different types of hypothesis tests. And you'll see it depends on the data type, what kind of distribution we have, and we're going to kind of get into all this stuff. So let me get into the steps. The steps are always going to be the same. And we're going to call this inferential statistics. All right. So descriptive statistics is we're kind of just summing up the data with mean, mode, median, standard deviation, variance, range, all that stuff. Now we're going to try to make some inferences, some guesses almost, some asking the data some questions. So the first thing we're going to do is clearly define the objective and the confidence level. So that's what that statement is above. Clearly define the objective. We want to know if July 7th is statistically significantly different than the average for the month of July temperature-wise. Decide whether it'll be in a confidence level, again, 95% confident. Then next is, are we going to test it using a one or a two-tailed test? And difference is pretty simple. When I see the word in my statement, if I see the word different, it's going to be two-tail. If I had said, was that day's temperature statistically significantly hotter than average or colder than average, then it would be a one-tail test. All right, two-tail means it's just different. It could be hotter, it could be colder. And then the next step is to formulate a null and an alternate hypothesis. And the way that's going to work always is my null hypothesis is a statement that says July 7th of last year was not statistically significantly different than the average for the month of July. All right, it's always going to be, that's why they call it the null. It's always going to be the status quo. So we have to prove that it was statistically significantly different, which is the alternative hypothesis. So the null is there's no difference between last July 7th and every other, and the average, it's not statistically significantly different. And the alternative is, yes, July 7th was statistically significantly different than the average for the month of July. And the only goal in hypothesis testing is for us to reject the null hypothesis. That's all we're trying to do. All right, that's it. Once we do that, then we pick we're going to select the test distribution and a critical value of the test statistic. And again, that's when we're going to get into, as we get into the PowerPoint, and we look at different types of data. This is going to tell us which hypothesis test we're going to use based on what kind of, we're looking at mean, we're looking at continuous data, which is data that we measure, not count. It's a normal distribution, but there's a whole bunch of different tests depending on what my data is. We're going to get into all that. So I select the test distribution, and each test distribution has a formula to it. Okay, so in this case, the test distribution we're selecting is a Z. So there's the formula for a Z distribution. We have a lot of data. It's normal. Let's face it. I mean, climate changes, I love to do from 1900 to kind of understand if is it statistically significantly different. But it's pretty bell-shaped, right? It's kind of like my weight. It's going to land it somewhere in that, in that bell underneath that graph. So the formula is Z is equal to X, which in this case is going to be 94 degrees. That's the one that in question, July 7th, minus the average, which is 87 and a half, divided by the standard deviation, which is 3.5 degrees, right? So I have everything in that question in order to do the formula, do the formula. So I do the formula, 94 minus 87.5 divided by the standard deviation, 3.5, and I come out with a z-score of 1.857. All right, so that's my test statistic. Calculate a test statistic from the sample. So that's what I've done. And now I'm going to compare that calculated value to a critical value. And a critical value is always going to be from a table, right? So in this case, there's a table for every single type of, I'm sorry for making you seasick if I am with the moving around with the mouse, but each of these hypothesis tests has its own table. So basically, we're going to look to see where are our goalposts. And the way we're going to look at, in this case, we're going to look into a t-table. And I have a z-score that I just calculated down at the bottom there. It's that last row. And my confidence level that I'm interested in is a 1.96, 95%. You see that? So in blue there, you can see 1.96. So I know my goalposts on the high end and the low end is going to be 1.96. So basically I drew, not too pretty, a bell-shaped curve with my jaggedy mouse. And I want to know, where is the rejection region? In other words, where is the point where I say, yes, it is significantly different? So on the hot side, I'm going to put a goalpost at 1.96. And on the cool side, I'm going to put a goalpost of 1.96. And then I look at my test statistic again, which was 1.857. And I can see that is 1.897 falls before 1.96. So it's in the spell, right? Before the rejection region. So largely the only thing it tells me is that I cannot, if it was in the rejection region, then I could reject the null hypothesis. Since it's not in the rejection region, it's in the body of the bell-shaped curve, then I cannot reject the null hypothesis. So 94 degrees is not statistically significantly different than the average for the month of July temperature since 1950 with a 95% degree of confidence. If I didn't want to have a 95% degree of confidence, I could pick any degree of confidence I want. So if 90 degrees was my confidence level that I chose, then my goalpost would be at 1.645. You see where I grab that? Down here. And so it wouldn't be 1.96, it'd be 1.645. Now it would, at 90% would be in the rejection region. So that's just a quick overview of how all of the hypothesis tests work. And we're going to probably do more hypothesis tests next week and the week after. But it's going to be the same steps, no matter what kind of data we have. It's going to be a different formula that we have to, we use, and it'll be a different table that we compare to get a critical value. So we have a test statistic, a critical value, a confidence level, which you're going to hear terms like alpha and beta. You're going to hear all kinds of, what it means is it's a rejection region. That's all. Statisticians love to try to confuse people. But if I love the idea of just, all right, those are my goalposts. All right. So once I set them up at 95% confidence, where does my test statistic fall? So that's just a quick overview. If it's kind of foggy or abstract, don't worry about it. Because again, I just want to introduce it today, and we're going to go through those same steps. No homework, so you enjoyed that. Any questions about that before I get into the PowerPoint?
No, thank you.
Right. Right. Congratulations, people. You're 2/5 of the way to a coffee mug
Woohoo.
and also a certificate suitable for framing. We're in the
Oh,
analyze
wonderful.
phase.
Ready for that.
Yeah. So again, we're in the analyze phase now. So define the problem and the objectives. What do we need to improve? Can we measure it? What's the best way to measure things? And now that we've got a bunch of measurements, now we're going to analyze it. Okay. And I think PTA, with the big setup reduction Kaizen they're doing, Ed's on it. I think Marcus, I don't know if Marcus and Meg are on it too, but they're pretty much done with measure now. All right, now how we analyze this? That's where we're at now. And in analyze, it's about finding the top one to three causes of the problem being addressed. And when we say problem in statistics, in Six Sigma, we're talking about variation, right? So what are the top one or three causes of variation? And it starts with the team inputting regarding potential causes and using statistical methods to isolate the top one to three. And here is the contents. We're going to talk a little bit about patterns of variation and a cool tool called multivariate analysis. We're going to get into different classes of distributions, and then we're going to get into inferential statistics. And I think we're going to get through reading tables today. So just kind of general concepts, introduction to hypothesis testing. And I'll kind of give you an idea of what's on the test and what's not on the exam, so you don't spend too much time um, pressing your mind. And then we're going to get into these tests next week, testing for normality, testing with normal data, uh, testing with non-normal data, so, also, with different types of yes, no's, votes, things like that. And these are all just different types of hypothesis tests. So it's going to be this analyze phase is heavy on hypothesis testing. And again, statistical notation. It's useful, just kind of refer to this when you're looking at formulas, like standard deviation we just did. Average is sometimes, the number, an X with a line over it. Patterns of variation, and again, multivariate analysis. The way I like to explain this one is variation in our processes can have like probably three types of sources, right? One is, let's pretend we're making cookies and we have day one and day two, and when we see variation, whether the cookie's harder or softer in the same batch or a different number of chips or walnuts, if you like to put in them, variation within the same unit is one. Two is between units. In other words, I make a batch of dough, and then I make another batch of dough, and I have differences between the two batches of dough. And then the third type is temporal, where over time I start to see variation. There's nothing on the exam about multivary. I just think it's a really cool tool because you can look at all those things at the same time. So basically, it's about visualizing various sources of variation. It helps us narrow down the number of X's that are causing problems. In this case, it might be, the oven temperature might be different between day one and day two, temporal, or it could be it's not evenly distributed in the oven. It could be my dough. I'm waiting too long to put my dough onto the pan, so that I'm getting the chips are selling out. Could be anything, stuff like that. But it helps us kind of think about what are all the sources of variation. It's a great tool for early root cause analysis, very similar to the one we worked on, FMEA, in terms of just getting people thinking about different variables, for sources of variation. And the cool thing is just a graphing tool. That's all. Multivariate. It displays the patterns of variation all at the same time. It could be within a subgroup, between subgroups, and again, it's positional, cyclical, or temporal. Within a unit, just think cookies. location in a batch process. It could be between units, consecutive pieces, groups of pieces, consecutive batches, or over time, shift to shift, day to day, week to week. Are we seeing this problem only on second shift or when people come in on Saturday? And it's a useful tool. And that's kind of what the graph looks like. You can kind of look at a whole bunch of variables at the same time. Nothing on the exam on this. I just wanted to make you aware of multivariate analysis. This one was really useful. My wife, when she owned the frozen yogurt shop, we were thinking about a second one. So I talked her into doing multivariate analysis. And we looked at store location, store size, and profit over the last 2 or 3 years. So we looked at all those three variables and without having to, and we kind of put them all together and make a good conclusion. And the conclusion was, no, we don't want a second one. Anyway, classes of probability, so different types of distributions. And these are the possible values a variable can take and how frequent they occur. The normal distribution is the one that we just kind of spend the most time on. It's the bell-shaped curve. It's for data that we measure. The total area under the curve is 1%, is 100%. I mean, it's shaped like a bell. It extends indefinitely in both directions and is asymptotic. What that means is if you look at the bell-shaped curve, we get into an area where there's what we call tails on the right and the left of the bell, where the rejection region was. You notice those weren't zero. There were still values there, but they're approaching zero. In my case of my weight, on the negative side, I'm never going to weigh 0 pounds, right? I guess if I corroded, I could weigh a lot, 0.5 pounds maybe. I don't know what a bones weigh, whatever. And on the other side, there's no real end in there too. I could weigh 1,500 pounds. So asymptotic means that there's no endpoint. That's all. The mean, median, and mode are the same. And you saw with the weight, it's pretty close. It's within a pound. And that kind of tells me, the process is in control, right? Or at least over the last, since 2006. And all processes will exhibit a normal curve shape if only pure random variation exists. For example, a polar bear weighs 500 pounds. How much does a polar bear weigh? 500 pounds, 500 kilograms. Well, in actuality, if I did a sample of 25, 50 polar bears, it's doubtful that any one polar bear is going to land on 500, but it's a bell-shaped curve if I have enough samples, right? It's going to come somewhere around 500. Same thing as how long does it take me to get to work? 22 minutes. Well, it doesn't really take 22 minutes. It might take 25, 19, 21 and a half, whatever. But when over time, once I have over 30 measurements, it's probably going to exhibit all the characteristics of a normal distribution, a bell-shaped curve. A student T is cool. It's the same general shape. Here, it's kind of this thing was a huge breakthrough because it lessens the impact of outliers due to a small sample, all right? But it's taking some math, combining a standard normal random variable and a chi-square random variable, which we're going to just kind of gloss over today. But basically what I like you to know about the student T is it's the same as the normal, but I don't have as much data. All right, so in the case of a normal distribution, if I have to get over 30 polar bears to weigh, the student T allows me to get 15, and it's going to kind of with the math involved in doing the student T, it's going to eliminate those outliers, which might be I have a pregnant polar bear, or I have a polar bear that isn't quite, is a young one, it's a baby or something. Over time, it's going to minimize the impact of those outliers. But it'll get me pretty close to a student T, a normal distribution. So now remember, the beautiful part about once I have a bell-shaped curve, I can do all kinds of math with that. Like becomes really useful in terms of making predictions and things like that. A binomial, again, now we're talking about discrete data. So continuous data is data that we measure, like weight, like stuff coming off our machines. Discrete data is stuff that we count. It could be votes. It could be, polls. It could be yes, no, how many yeses, how many nos, that kind of thing. The binomial distribution applies when the population is large and the sample size is small, compared to the population. For example, running an experiment several times in a row, flipping a coin 3 times, what's the likelihood of getting heads 2 times out of the three? And using a binomial distribution, I can predict that. And that's where gambling uses that a lot. Poisson distribution, it's a distribution for defect counts. Again, how many defects do we have over the course of a day, a week, a month? And it can be used as kind of an approximation to the binomial. It's the way to see how unusual an event frequency is for a given time period. All right. Here's an example I put. Jason Tatum is averaging 35 points a game. What's the likelihood he'll score 12 points in the first quarter of his next game? And then an F distribution is used extensively to test for equality of variances from two normal populations. All right, so we're looking at the equality of variances between two comparing two things. And the distribution of findings serves as a precursor for the two-sample t-test. That's very sensitive to non-normality. And an example is you're testing a new drug for a heart disease called X. You want to determine the significant effects of different dosages. So you set up trials of 0, 50, and 100 milligrams of that particular disease in 3 randomly selected groups of 30 each. This is where we use the F distribution. Anytime you're comparing more than 2 groups, and once the F statistics calculated, you compare it to a table, just like we kind of just did, with the T table and the test statistic. Chi-square distribution for multiple hypothesis tests, like the equality between the variance of a normally distributed population and a specific value. And also and don't worry too much about these. These are kind of just flying over ones that aren't in the test, the exam. Just kind of give you an idea of the different types of data we can make talk. So in the case for chi-square, market researchers use chi-square when they need to estimate how closely an observed distribution matches an expected distribution. Yeah, so inferential statistics, that seems to be the theme today. Statistical inference is the process of making inferences, making data talk of an unobserved population based on a sample. So in the case of the temperatures, we had a sample. My weight, not weighing myself every second, just Fridays as soon as I get up. It's a sample. Most of the time, we want our sample to do the talking for us because it's impossible to get the whole population. Costs too much money, it's not practical, and it's used because it's difficult to collect the entire population. Statistical inference contains 2 elements. What's the inference and what's the measure of validity? So here's the steps that we just went through on the two-tailed test for temperature in July in Connecticut. Define the objective. Is it 1 or 2 tails? Formulate a null and an alternate. Select the test distribution and a critical value, which comes from a table. Then calculate a test statistic from the sample, and then compare it to see if the null hypothesis is rejected or not. This is like the second time we've gone through these. It's going to be a couple more today. But anyway. And the outcome or conclusion of statistical inference is a statistical proposition about the population. So I can infer something important about it. Okay. Examples are estimating a population parameter, identifying a region where the true population would fall. It allows us to start to be able to predict, right? Because I think for data that we collect, we want to know, A, is it capable of what we want it to do? Is our process capable of doing what we need it to do? And 2, is it predictable? So I can once I know my data is predictable, then I can use hypothesis testing to start making predictions. Sampling, there's a whole science too. In statistics, they turn this into rocket science too. But it's a population is the entire set of observations and which one's interested in joining. It's every whale in the world about making generalizations based on samples. The process of selecting a subset is sampling, and we want to be able to have a sample size that reflects the population. Okay, we want to have enough sample to be able to make conclusions that would apply to the entire population. The sampling advantages is impossible or impractical. This is so redundant, isn't it? I didn't make these slides. This came from the Association of Statisticians or whatever. It's high cost, time consuming, whole bunch of disadvantages, but lower cost, faster data collection, easy to manipulate. So obviously we want to sample. And two major uses, estimate the population parameters, and two, be able to do some hypothesis testing, testing a statement about the population characteristics using sample data. These are the basic sampling strategies. I told you they turned this into rocket science. Simple random sampling, match random, stratified, systematic, proportional to size, and cluster. So we'll go into each one quickly. Simple random. Each item in the population has an equal chance of being selected. There's no bias involved in sample selection. We just go and grab some. This selection minimizes variation between the characteristics of samples in the population. Okay. And it's the basic sampling strategy. Match random is things that we want to do in pairs. Researchers are interested in understanding the weight of twins. Researchers are interested in understanding the patient's blood pressure before and after taking some medicine. So we're going to sample before and after. That's match random, obviously from the same patient. Stratified into distinct and independent categories. An individual category can be considered as a subpopulation. So stratified samples are randomly selected in each category. They can be gender, region, income level. And again, this applies, I think, a lot in polling. You know, if we're looking for what's a statistically significant sample and doing polls, I might want to do it by gender, region, income level, etc. It requires advanced knowledge of the population characteristics. Example is a fruit store wants to measure the quality of all of their oranges. They want to use stratified sampling by region to collect sample data. Since 40% of their oranges are from California, then 40% of the sample is going to be from California, maybe 30% from Florida, whoever else grows oranges. Systematic sampling, regular intervals based on an ordered list where items in the population are arranged according to a certain criteria. A random start, and then every blank item this is where SQL lands. You know, every 7th, every 100th, every 500th, we're going to sample. Commonly used in the quality department. Cluster sampling, samples are only selected from certain clusters or groups of the population, and it reduces the cost and time spent on sampling, but bears the risk the selected clusters are biased. So, for example, selecting samples from the region where researchers are located, so the cost and time spent on traveling is reduced. Probably the least favorable methodology in sampling. And sample size, this is a whole nother science. This is not on the exam. You guys are probably asking, what the heck is on the exam? Well, you're going to see pretty much the exam before you take it. So, but there's nothing, they turn this into science, like I said, into calculus, but the smaller the sample size, the higher the risk. The sample is not going to reflect the population. Greater the sample size, the more time and money we spend. There's actually an equation for continuous data that we can measure, right? Continuous means data that we measure, like weight, parameters off the machine, stuff like that. Here's the formula for it. The z-score at sigma divided by 2. So when the confidence level is 0.05 or 95% confidence, the z at 0.975 is equal to 1.96. That would go there. The estimated standard deviation, desired margin of error, and the number of samples. So there's actually, the only thing here is with this particular formula, it's when I have 30 samples or more. I probably never use it. Never, I don't think. But if you ever do, here it is. You'll have it on your slides. And if the calculated sample size exceeds 5% of the whole population, then you can discount that using the following equation. For discrete data, which is data that we count versus measure, continuous measure. That's something I'd really like you guys to grab onto. So discrete data is things that we count. Here's a formula for that. And if it exceeds 5%, then you use this formula. Sampling errors. A random sampling error is due to observations being selected randomly. It's inherent in the sampling process and beyond one's control. I mean, we can just, if we're sampling randomly, we might get an outlier or two. That's going to happen. I might get a baby whale. I may get a pregnant whale. Who knows? Selection bias, non-random variation due to inadequate design of sampling. And it can be improved by adjusting the size and sampling strategy. So I guess the point there is that sampling isn't as simple as we think sometimes, because when it comes to statistics. All right, now back into hypothesis testing. General concepts, going to be a review for you. I'm going to try to make this as simple as possible so I can understand it. It's a method where a specific hypothesis is formulated about a population, and the decision of whether to reject the hypothesis is made based on sampled data. That's what hypothesis testing means. And it's formulated in pairs: a null hypothesis, HO, which is the status quo. And in other words, I think about it as innocent until proven guilty. And the alternative hypothesis, HA, is going to be what I have to prove. And I have to try to disprove the null hypothesis. That's all I'm trying to do. So in this case, the null hypothesis was that 94 degrees is not significantly different than the rest, statistically significantly different than all the data. And the alternative was, yes, it is. And that's as simple as it is. It's just the null is always going to be status quo. It tries to answer whether there's a difference between different groups or there's some change occurring. Some examples: if I have average SAT scores of two high schools, are they the same? Statistically, significantly the same or different? Is the error rate of one group of operators higher than that of another group? Are there random causes influence the height of kids in one state? These are all kinds of questions you can ask of the data. When we get into my weight data and we get towards the final presentation, one question might be do my health statistics change during the holidays or during football season, or am I fatter after Thanksgiving? You could do all kinds of answer a lot of questions with the data using hypothesis tests. And there we go again. The null hypothesis: no difference, no changes, and the sample observations are from random chance. Alternative: there is a difference in the measurement. Oh, here we go again. I told you we're going to pound this into you guys, right? Two possible conclusions: when there's enough evidence based on the sample to prove the alternate hypothesis, we can reject the null. If there's not enough evidence, because we did the math and compared it to a critical table, then we fail to reject the null, kind of what we did with that 94 degrees. Now, practical versus statistical significance. An observed difference is practically significant when it's large enough to make a practical difference. And that might be temperature, right? The difference between 85 and 95. There's probably a practically significant difference there. But it may not be statistically significantly different. We got to do the math to figure that out. In some business situations, statistical differences can have little or no meaning because the difference is not large enough to be practical for a business to act on. In statistics, an observed difference is statistically significant if it's unlikely the difference occurred by pure chance, given a predetermined probability threshold. So we use the probability threshold of 95% confidence, right? Statistical significance indicates there's some non-random factors causing the result to take place, and the statistical significance level in hypothesis testing indicates the amount of evidence which is sufficiently persuasive to prove that a difference between groups exists, not due to random chance alone. Again, the confidence level is all really going to take from that. And again, you got to pick that ahead of time. Say, hey, I want a 90, 95, 99% confidence. And we pick 95 for that temperature. And you can pick anyone you want. Probability refers to the likelihood, the chance or possibility of an occurrence. So the probability of any event lies between 0 and 1. the sum of all probabilities of all possible events in a sample space is equal to 1 or 100. Probability is always a ratio, the ratio of chances of event success versus the total number of ways an event can occur, not on the test. Example of probabilities, a die has 6 sides, so it has a sample space of 6. Each face is unique. Thus, each time we roll a die, there's a 1 in 6 chance that it will land on any specific number. So there's a 16.67% chance that every time I roll a die, it's going to come up a certain number. So I wanted 2. Well, 16.67 chance that it's going to come up a 2. So 1 out of 6, 1/6 equals 0.1667 to get a percentage of go times 100. Now, what's the probability of getting 5? I'm going to say 2s in a row because I just said 2. You could say probability is 1, which is 0.1667. 5 times 5 equals 0.1667 times 5 is I have a 0.013 chance, 1.3 chances out of 1,000 that I'm going to get 5 of the same number off the die in a row. And calculated probability allows the establishment of acceptable risk, and that's where gambling comes in. Whether it be a slot machine or roulette, it's all based on probability. Probability that they got to give you their money. A p-value is the difference between observed data and claims made under the null hypothesis may be real or due to chance. A p-value is a probability of these differences solely due to chance, random. The alpha level, the level of significance of a test, represents the threshold against which p-values are measured. Alpha level versus or A is adjusted later. The null hypothesis is rejected if the p-value is less than A. So, and that's kind of what we just did. Just forget this slide. Just think about what we did with the temperature. The most commonly used levels are 5, 10, and 1%. So p-value is no different. It's another, the statisticians love to talk about p-value. It's no different than confidence level. So if a p-value of 5% is a 95% confidence level, and a p-level of 10% is a 90% confidence level, and a p-value of 1% is nothing more than a 99% confidence level. Just a different way of saying it. So I just like to stick with 1. So p-value, same as confidence level. Types of risk. A type 1 error is a false positive, a false alarm. It's called an alpha error. A type 1 error is associated with the risk of accepting false positive. It occurs when we think there's a difference between groups, but in fact there is none. So in other words, we do the hypothesis test and we find that we have a type 1 error. It's like telling a patient that he or she is sick when in fact he or she is not. That's a type 1 error. Alpha and confidence interval. Alpha indicates the probability of making a type 1 error. It ranges from 0 to 1. 5% is the most commonly used alpha. 100 minus alpha, 100 minus 5% is the confidence level which we use to calculate the confidence interval. So it's the same thing. Just think confidence level. 90, want to be 90% confident, 95. And again, you get to pick those before you do your test. Decision rules. When making a decision on whether to reject a null, we compare the p-value against alpha. If it's smaller than alpha, we reject the null. If it's greater than alpha, we fail to reject the null. And that's kind of what we did with the rejection region. The p-value was less than what we pulled out of the table, that 1.96. I'm sorry, the other way around. Because we failed to reject the null on that one. Forget p-value. Type 2 error is false negative, oversight, or beta error. It's the risk of accepting false negatives, telling a patient he is not sick, and in fact he is. Not on the test. And then the same thing with beta is same opposite of alpha. It's a chance, but it's the probability of making a type 2 error. And again, it's the same mindset, 100 minus B. So again, confidence level. Just think confidence level, forget alpha, beta, anything else as we move forward through these tests. Confidence interval is an interval where the true population parameter would fall within a certain confidence level. A 95% confidence interval indicates the population parameter would fall in that region 95% of the time. It's the most commonly used confidence level. That's the one you're going to see we use the most as we do some exercises. And again, guys, this is just mind-blowing a little bit, these slides. Really, what I'd like you to just take from this today is just what we did with the temperatures, because it's going to apply to every single test we do. The width of the confidence interval depends on the confidence level, the sample size, the variability in the data. The higher the confidence level, the wider the confidence interval. So the rejection region gets moved, on the right gets moved farther out. If it was at 99, and same thing on the left. The smaller the sample size, the wider the confidence interval. The more variability, the wider the confidence interval. And here's the rejection region we talked about. These are our confidence levels, our goalposts, rejection regions in black. And types and decisions. All we need test statistic versus critical value. So test statistic is that little math problem that we did on the temperature. Critical value is what we took out of the table. And then the p-value versus alpha, that's the confidence level that we chose. In the case of temperature was 95% confidence. Here's the test statistic. It's it's that little math that we did. It's a value calculated using a function of the sample. Different hypothesis tests have different formulas. And the test statistics are the sample data's numerical summary that can be used in hypothesis testing. And we note it as test calc or test stat. Critical value is what we take out of the table. It's the threshold value to which the test statistic is compared. It's obtained from tables. There's a different table for every type of hypothesis test. So the trick is really in knowing what kind of data do I have and which test do I select. That's really the only trick to hypothesis testing, which we're going to kind of get into over the next couple of weeks. Decision rules, again, when the test statistic falls in the acceptance region, then we fail to reject the null, which is what happened with the temperature. We could not reject the null because it fell into the acceptance region, not in the rejection region. And we can claim that there's no statistically significant difference between the groups. When it falls into the critical region or the rejection, I like to think instead of critical region, think rejection region, because then I can reject the null. And again, I'm going to skip this because it's the same thing, just different terms. We did talk about two-tailed versus one-tailed hypothesis tests. Two-tailed, all I want to remember is it significantly different? One-tailed, is it hotter or colder? So it's one side or the other. Hot would be on one side of that graph, cold would be on the left side of that graph in terms of temperature. I want to know that before I do my test. And here's the two-tailed test. When they're between groups, we don't care about the direction of the difference. We don't care if it's hotter or colder. At 94 degrees, all we want to know is it different? I think everything else is a review here. And my alpha or my confidence level is 95%. And there's the tails in black. Does my test statistic fall inside the acceptance region or in the rejection region? That's all. Same thing for a one-tailed test, except we'd only be looking at is the question my null hypothesis would be that 94 degrees is not statistically different, is not significantly hotter than since 1950. Right, so then I'd be only looking at this end of the curve. Same thing with lower. And reading tables, all we need to know before we use them is what kind of distribution we're looking at. So we're looking at a bell-shaped curve. What significance level, not alpha, I called it 90 confidence level is what I call that. 95% confident, we want to know. We need to know sample size. Degree of freedom is the sample size -1. Fancy way of saying sample size -1. We need to know if it's right tail or left tail. And then we plug it into like we did. We did one for the z value. And here's all kinds of You can just Google any kind of table you want, and they're all there, depending on the kind of test you do, the kind of data you have. And that's again, that's what the trick is picking the right formula and the right table. And we're gonna do a little bit of practice on some of those. So how to read it. We did one, so I could skip this. And that's it. Whew. Told you it was ugly, right? Today. We're getting to the top of Everest. All right. And again, most of the stuff, I think the key takeaway today is that first 5-10 minutes that we spent in math practice going through, those 6 steps of how to do a hypothesis test. Now, next week, we're going to get into all the different types of hypothesis tests, depending on what kind of data you have and how to use it. I apologize for the filibuster today. It's just part of the course, so I had to get through it. So any questions, thoughts? Everybody still with me? Nobody's going to resign today?
Yep, still here.
All right. All right. All right.
Still here.
Have a great night. No homework if you haven't done it. I mean, everybody's pretty much done. But if you haven't done it, you got another week to do it. So talk to you. Have a great night, you guys.
You as well.
You too.
Thanks,
Bill. You
Bill.
too.
You.
Bye.